Hello, and welcome back. This is day 6, so we kind of skipped day 5. Um, again, real life kind of gets in the way, but I guess I can talk about the P5 solution real quick. So this is what I came up with. Basically, yeah, so if we look at the logical place to start would have been my P2 solution, but the more that I look at this, I am not really a fan. This is a very sort of imperative style. I don't think that this is, super extensible. And considering that I imagine the int code computer will be used again in future problems, sort of wanted to start over and build something, build something that I could easily extend for future problems. So that was sort of my goal with this. I was inspired. I saw Jay Fode's day 2 solution where he used this sort of recursive idea where you're passing the index on the left and then you're sort of modifying the different, modifying the states and passing a copy of that in the recursive call. I kind of like this. I used a multi-line function, which I literally don't think that I've used in Dyalog before. It's kind of interesting. Yeah, and I just wanted to make this R, R for run. I wanted to make this as self-contained as possible so that I could extend it and place it into future solutions. And I mean, we can go over it a little bit. I think most of this is I posted a version of this where these opcodes weren't grouped together like this. This is just something that I kind of did for fun. But it's also totally fine to just check the opcodes individually. And let's see, maybe the only super interesting thing going on here is just how I put together the modes and the parameters. So I basically put them in a 3-row, 2-column matrix. And then I only take from that matrix the number of rows equal to the number of parameters that we're looking at, because you have to be careful about index errors. So you can't just assume that you can't just get 3 parameters each time and then check the immediate and positional addressing modes, because if you're dealing with an opcode that only takes 2 parameters, I guess this would be opcode 3 or 4, then if you try and index into that third parameter, you might get an index error. So we're just making sure that we're only taking the parameters that we're actually operating on. We select reduce across the rows, and then we take 3 elements. So again, if we only pull 1 parameter, we take 3, and then we assign these out just so that everyone's on the same page. If you take more elements than exist in the list, like if we have a list of 1, 2, and we take 3 elements, it pads it with zeros, at least for numeric vectors. Yeah, and then we basically just recurse. We have in for the next index we want to hit, and yeah. In the future, we are probably going to have to extend this so that we take multiple inputs. This was actually, I was talking with Daniel Fuckman. What was his? Sorry, I forget your last name. But I was talking. He mentioned on Reddit also that we'll probably have to take multiple inputs in the future, and I don't think that that's too big of a change. That's basically which opcode is it? Opcode 3 here. We can do something where we basically just drop the first element from the input, assign that to input, and then we can sort of recursively call for opcode 3 here. So I don't think it should be too bad. And this makes it easy to add additional opcodes. So yeah, I don't know. That's my P5 solution. Didn't have a video for it, but I'm pretty happy with how it turned out, and it should be extensible for future problems. All right, so without further ado, We can go to problem 6. Let's see. Blah, blah, blah. Center of mass. Ooh, orbits. Are we doing trig? I did there's another contest, the International Conference on Functional Programming. They run a contest, the ICFP contest. I did that in, oh geez, it must have been, what is that, like 11, 12 years ago? I did 08 or 09, where it was based on celestial mechanics. You had to do like Hohmann transfer orbits and stuff like that. That was a really interesting year. To verify maps, direct orbits and indirect orbits. Okay. And we have a DAG here. Okay. This is kind of, so last year for Advent of Code, we had some sort of problem about like elves assembling components. What was that? Is that day 7, I think? Where you basically had to do a topological sort on these dependencies. This is the same sort of idea, but a little bit different. D directly orbits C, L directly orbits K, COM orbits nothing. Direct and indirect orbits in this example is 42. Okay, so D orbits C, indirectly orbits B and COM, total of 3 orbits. So 1, 2, 3. Yeah, I guess. So I guess the idea here is basically you just kind of run through all the different elements. You do like a depth first traversal down to COM, and you just count how many times you do that, and then you sum all of it, pretty much. And there's some fancy things you can do. You can like memoize these calls so that you're not recomputing it each time. I probably won't do that on the first pass at least, but maybe it's something that we can look at. Yeah, okay. And what does our puzzle input look like? Yeah, okay. Well, we're going to start out with the test case then. Alrighty. We will add /test.text. Yes, please. And all right, so we will, as usual, start with parsing. Let's get our solution file going. So for parsing this, basically we split on the right parens character, so we'll just do the same thing that we usually do. So this will be inget test.text to start with. We'll change this later to our problem file. We take the first element, and this is like this. What is it? Not equals /2 underbar right. Ah, that's interesting. Oh yeah, I haven't. This behavior in RIDE is really annoying. If anyone's watching and knows a way that I can save files without having to close, that would be great. So what is going on here? Oh yeah, that's for each. My bad. Yep. How was if I mix these? Yeah, seems good. Okay. And then we will call this, what's the shape of this? Just so I'm not crazy. 11.2. The shape of the first element is 3, so that is the string. All right, cool. So we'll assign this to Pete. And we'll put it here. Okay, so let's see. So I don't think, so the right column lists out all of our elements, right? And I think if we look at this thing, so if we look at this, it's basically a directed acyclic graph. We shouldn't have any duplicate elements in the right column. And this matrix basically says element on the right orbits elements on the left, right? Okay. Okay, if we bring all these together and then we transpose it, now let's split it like this. I guess that's pretty much, no, that was the right idea. So if we transpose it and we split it like this, then we get the list of the individual columns. And we can actually call this like, so the first column will be destination, and this will be, second column will be source, right? So because in APL we don't have native support for dictionaries, essentially what I'm thinking is that when we do our traversal, we'll get the index of the element here, and then we'll index it into this array. So index of in source, index into destination, right? Yeah, okay, cool. And what would the traversal function look like? Well, if we say w match com, then we return 1. That's like our base case. And otherwise, we'll say source index w, destination index, like so, recurse. Maybe. Oh, and then, yeah, so we'll do 1 plus, right? We'll call this F. Okay, great. So if we take D directly orbits C and indirectly orbits B and com, a total of 3 orbits. Okay, so if we take FD, yeah, well, that's my index origin. Okay, so let's work through this. So the index of D in S, oh, it doesn't, huh. What's going on there? So you're telling me that the third element of S, oh, yeah, sure. Okay, that's kind of gross, but fine. So we enclose it. No, still? Huh. It's just a scalar. If I disclose it, I get this. It's there. Oh, it doesn't. Yeah, there's some. There's some trick to this. What was it? I get tripped up on this sometimes. Is it nest? Oh, okay, it's treating D as a scalar because it's a single character. So if we, yeah. All right, fine. Great. Yeah, okay, so it's saying, basically the problem was, so if we take the third element from S, and we disclose it, and then we take the shape of it, it is actually a one element list, which makes sense, I suppose. All right, so we'll take enclose ravel omega. Now if we say FD, same deal. Okay. Well, so if we do this and we say D index like so, we get C. Oh, but now, yeah, okay, fine. We'll say we don't have this in the function itself, and instead we will ravel enclose D. Really? Okay. Well, let's do some old style debugging. Like so. CBCom. Oh, gross. We have to enclose com as well, I think. 4. So there should be 3, which means that this should be 0, like so. CBCom. All right. We got there, folks. It's kind of rough going. Yeah, all right, cool. And then basically the idea is so we'll say that we have a sum of 0, and then for each source, we will do f. Ooh, this might actually be, so because it's coming from S, they might already be enclosed and raveled. And we can just do a sum like this. Rank error. Now that's interesting. For each S, just give me the element. What am I? All right, fair enough. Sorry about that. Yeah, I have to manage my variable name's a bit better. So we'll say source dest, like so. And now we'll say something like this. So for each f, still rank error. That's because I haven't updated my function. Source dest, like so. Now we're back at index error. Okay, once again we will debug, and we don't even get to the first one. So this seems to imply that we do need to rabble enclose W and apply F to it. 42, there it is. All right, great. I don't even know, like, I was planning on using some here, but I actually don't need it at all, which is sort of interesting. All right, cool. Let's take, so F, we will say F equals this thing, and then our, right, and this has to be, oh geez, where did I assign dest source? Yeah, something along these lines. Okay, great. 42. So let's get our puzzle input. Yep, and we'll just say po6.text. Great. There it is. So if we change this, I hope that assumption that I made about the right column being unique is accurate. I guess we'll find out. 142, 497. It's a little bit slow, and like I said, we can speed that up by memoizing it. Yeah, that's good enough for now. How many orbital transfers you in parentheses need to take to get to Santa? Oh, gross. Yep. All right. An orbital transfer lets you move from any object to an object orbiting or orbited by that object. We're going to rescue Santa, guys. For example, suppose you have the following map. Visually, the above map of orbits looks like this. Fair enough. Not between you and Santa. Okay, so how do we do this? Um, we can build a list. So basically, like, let's say that you're traversing from I down to com, right? What we could do is we could say we could build a list where basically for index D we have a matrix that says, hey, for all the elements that feed into here, here's how far away they are, right? And at the end of that, we can traverse from U, and we'll keep going until we hit a table that contains Santa. All right, so we'll add along the way. And then once we hit this table, we can just pull the value and that's it. I mean, really this is a, I mean, this is just a graph traversal problem, right? Now this is not a DAG. Now this is a full graph. So, man, there's something kind of fun in, let me think. I could render this as a graph and then do breadth first search, right? That would do it. I kind of want to check this out. So if we look at the Dyalog defense, which are, this is kind of like, sort of like the standard library. These are basically like extended functions that people have written for common tasks. So you have stuff for like working with arrays, trees, graphs, strings, all sorts of stuff in here. I encourage you to take a look at it if you haven't already. And in here, we have path. Shortest path between W and graph A. But the problem for this may be a vector of vertices. Graph A, shortest path from 4 to 3. So what constitutes a graph? So they use this format like, let's look at this one. Classic breadth first search. Yeah, that's cool. Oh, I see. So it's just a, so like at index 1, you just have a list of vertices, right? And then index 2 here, you just have 1, 3, and 6. Then at index 3, you have 2, 4, and 7. Uh-huh. Okay. So what if, I don't think that, like, this is maybe not the shortest way to do it, but I'm kind of having fun because I like some of these defense functions. Um, yeah, all right. So we can say, let's go back to you know, our test function here. And we'll say, hello cat. My cat just jumped up on me to get some pets. Yeah, so that's test.text. That's cool. And okay, so if I do this, now let's say that we're going to build a graph. So our graph is going to be source row Zilda. Would exceed, what's the, oh yeah. Jeez, sorry. Length source Zilda row commute. And we get a big fine. Enclose Zilda. Yes. So we get a big array of, oh, yeah. Not that big, please. Good. So we get an array of empty lists. And then basically what I want to do, so if we mix dest source like so, and we transpose it again like this, then I believe maybe it's faster to do iota link source like this, and we will do for each g sorry, append was going to be w cons dest index of w. Wait. No. Dest index of source w. that might have done something. It did, but stupidly I forgot to index into G. But maybe that's okay. So if we just set G as like Zilda, and then we do this, then we get something like this. But that's still not what we want. So okay, so I will go back and do our original definition of G, and then we'll say GW cons length there. Because it gives us a disclosed array. I see. I see. Okay, what about this? Calm down, cat. I don't know if you can hear her or not. She's purring pretty loudly. How about this? Still a link there. Oh, because we have to enclose it. Now we're getting somewhere. But the problem is, so in this graph, so if we look at this, this is basically a graph of this is a graph where all the vertices have two elements. There are plenty of vertices here that have more. So what am I doing wrong? Calm yourself, Velma. Ah, right. This is only half of it. This is only half of it. So first of all, we'll take this off. Oh my goodness. Actually, let's just go ahead and get this out of the way right now. Yep, okay, this seems more like it. And then we also need to let me think about this. So if you take our first one like so, let's just roll with this for a second. I mean, what we could do is we could just do a secondary function here where basically we just reverse source and dest, right? Let's try that first to make sure that we're actually on the right track. So for each length in dest w, source I, yeah, like this. Better, but we still only have two. Well, yeah, of course. I mean, this idea here is not, that's not going to work. So instead, oh, wow, that's weird. So we have our source. And we've got empty graph. And what we'll say is for each one of these pairs, no, so you have a 2-element list. Basically, we'll say that source I is like no, no, no. So for source index of both elements, I think that'll be okay. Let's just try this first. Yeah. We can assign these to A, B. And then we'll say that GA, we have to do the annoying disclose thing. But then we can do BGA assign and vice versa. So we'll do GB assign A disclose GB. Really? Okay. What if we do this? Then we disclose. Then we take the unique. It's one of these. Yep. Like so. And this will be, are we using n? I don't think we are. This will be n for nodes. And this up here is going to be node index w, because it didn't have com before. Still linked error. Oh, linked error is actually better than index error. I'll take it, because we have to enclose those. But now we get index error again. So if I look at this, let's say that I take the first element and I say in index of this 1, 2. Makes sense to me. Huh. Oh, my graph. My graph needs to change. All right, so we have speed length in now. Then we'll do this. Yep. Yep. There is a simpler way to do this, most certainly. But I don't know what it is. That's okay. All right, so I could just this relies on a lot of other stuff in the defense namespace. So I thought I could just take the function, but I probably can't. So I'm gonna have to download the whole thing. Which is fine. This is the one I want. And then I think I can just do load defense.dws. I think this will close all of my text windows, which is fine. We keep CD and everything. All right, so if I do this, I'll do both of these. This whole line here. What if I named n? Yeah, I guess that makes sense. Where did I define n? Here. Yep, and then do I have path? I do have path. So for gpath, in index u san. This is the shortest path. Great. And if I take the length, I get 7. And the actual answer is that it takes 4, but 1, 2, 3, 4, 5, 6, 7. But we're moving from K to I. So I think if I just take the value and I subtract 4, 1, 2, 3, 4, should be okay. Huh. All right, I kind of want to test it. P06.text. How big is it? We have 1,058 unique nodes. And we've got a big graph. Just for kicks, how densely connected is this graph? So for each graph length, yeah, 2 elements, 3 elements, something like that. All right, and then if we do this and we subtract 4, $300. I mean, I don't know. Let's find out. Your answer is too low. Let's go back to our test. So we have this, we have this. Right? This is pretty simple. And if I do the path from, let's say, like E to com, I am expecting that to be 5. Oh, wait, did I got the constant wrong. So it's 7 here, it's 4 here, so I should have subtracted 3. And then I think the answer would have been okay. Why is it 3? Or why am I subtracting 3? So in reality, I'm starting at K, and I'm going 1, 2, 3, 4. I guess that makes sense. Yeah, 1, 2, 3, 4. These are the actual orbital changes that I'm doing. Right? Okay, fine. Since we have a little bit of time before the website timeout comes back, let's just see. Okay, so we have inget test.text. And then if I wanted to do a path from, let's say, F to com, right? So in F com path G. That's interesting. Huh. Index error. Test in G. Well, okay. Let me just try 301 first. All right, because we should have subtracted 3, we subtracted 4. That is the right answer. Great, I guess. Okay, I don't really know what's going on there. If I go from U to Santa, I get this. All right, anywho, let's edit our, not that one, this one. Oh my goodness. I didn't save it. It closed my window without saving. All right, fine. We can reconstruct it from our history. What was F? F is like this. So okay. Oh, like this. Fair enough. $54. Oh, this is new test data. So I guess if we do PO6. Yeah. 42, 497. Okay, great. And then I'm just, we'll simplify this, of course. Because that's a little unwieldy. And then what are we doing? We're doing G path like this, length 3 minus. Yep, so that's the big one, and then 301. Okay. Source const test is this. So this can easily just be like so. And then you really want seems like you want to maybe like this. Rather than reading the file again. We'll give graph its own line. Length error now. Well, what's the difference between that one and this one? Oh. Right, so this is split. Index error. But if I split this, oh, okay. Fair enough. Yes, these two are backwards. Great. Still index error. It's very strange. But it works with this. That's what you're telling me? Uh-huh. Oh, jeez. Yeah. I was just missing that disclose. Okay, and this graph building function, I feel like we can do something better here. Maybe not. This video is already getting a little bit long. But yeah. So I guess, I don't know, the takeaway from this is that there are many useful functions in the defense namespace. So you have path, search, rim node, etc., strings, words. Yeah, many of these are really quite nice. Yeah, binary search trees of various types. So if you need to do anything with data structures or Shannon entropies, yeah, here you go. This would be the place to look. Anyway, hopefully this was helpful. I don't know, we sort of went all over the place, floundered around a little bit, but you know, we got the answer in the end. Thanks for watching, and I'll see you next time.